Hello everyone, I'm going to present counterexample guided synthesis of neural network Lyapunov functions for piecewise linear systems. In this paper, we are interested in proving the Lyapunov global stability of a dynamical system. Namely, all trajectories should converge to the equilibrium. This property is certified by a Lyapunov function, which is a bowl-shaped function. For example, the function shown on the bottom right is a Lyapunov function for the damped pendulum. The function is strictly positive everywhere and also strictly decreases everywhere. We aim to synthesize such a function to prove global stability. There has been an immense body of research on synthesizing Lyapunov functions. For example, there is an optimization-based approach that for a linear dynamical system, we can solve linear matrix inequalities to find quadratic Lyapunov functions. While for polynomial nonlinear systems, we can solve sum of squares optimization to find polynomial Lyapunov functions. Recently, with the fast advancement of deep learning, people started to represent Lyapunov function through neural networks. For example, Richards learned the Lyapunov function and region of attraction using deep networks, but didn't verify the Lyapunov condition for every state. Recently, Chang and Abate learned the Lyapunov function as neural networks and verified the Lyapunov condition through SMT solvers. Their approach is to first train the network over a finite set of samples, and then verify the Lyapunov condition using an SMT solver. The solver either reports a condition satisfied or generates counterexamples, which are appended to the training set. Our approach is similar to their approach in that we also use a neural network and we verify the Lyapunov condition. But first, instead of using an SMT solver for verification, we solve a numerical optimization problem, specifically a mixed integer linear program. Second, instead of just using the counterexamples as the training set, we also compute the gradients of the violation of the Lyapunov function through the optimality condition of the mixed integer program. We will show that this approach speeds up the training. In this paper, we are interested in a special type of dynamical system, the piecewise linear system. This is a hybrid system that the domain of each hybrid mode is a polyhedron conic region, and within each hybrid mode, the dynamics is linear, as shown on the right figure. This hybrid linear system is often used to approximate nonlinear systems. We consider both continuous time and discrete time cases. Previously, to prove stability of a piecewise linear system, people first attempted common Lyapunov functions. Namely, all hybrid modes share the same Lyapunov function. Unfortunately, many stable piecewise linear systems don't admit a common Lyapunov function. Then people proposed piecewise Lyapunov function for more flexibility. The limitation is that it is not clear on how to choose a domain of each piece in the piecewise Lyapunov function. A popular choice is to align each piece of the Lyapunov function with each hybrid mode of the dynamical system, namely one piece per mode. Again, this choice is so restrictive that it often fails to find the Lyapunov function. It is worth mentioning that people also propose algorithms to automatically find the domain of each piece. The general idea is to first partition the state space into small regions and synthesize a Lyapunov function on each region. If such Lyapunov function is not found, then the algorithm continues to chop each region into finer pieces and synthesize the Lyapunov function again. So the algorithm uses this iterative process to find the Lyapunov function, and within each iteration, the domain of each piece is fixed. Our goal is to come up with an algorithm that can freely search over both the domain of each piece and the piecewise Lyapunov function jointly through optimization. Our approach uses a fully connected multi-layer perceptron to represent the Lyapunov function. We denote the output of the network as V theta x, where theta is the width of the linear layers. We use leaky ReLU as the activation function, and we draw the leaky ReLU function on the top right. As you can see, it is a piecewise linear function. Since we only have linear layers and leaky ReLU layers in our network, the Lyapunov function becomes a piecewise linear function of the state. This piecewise linear relationship is very important in our analysis, as we will see shortly. Let's revisit the Lyapunov condition. First, we have the positivity condition on V theta x, and that Lyapunov function goes to infinity when the state goes to infinity. This is equivalent to requiring that V theta x is larger than the scaled one norm of the state. We also impose the exponential stability condition on the time derivative of V for both the continuous time and discrete time systems. These are the conditions we want the Lyapunov function to satisfy. We will show that we can efficiently find counterexamples to these conditions. Let's use the positivity condition in the boxed equation as an example. We can move V theta x to the right-hand side of the inequality. And to find counterexamples, we maximize the term on the right-hand side. If the objective of this maximization is greater than 0, then we find a counterexample. If the objective is 0, then we prove that the positivity condition is satisfied. Similarly, we can find a counterexample to the Lyapunov derivative condition by maximizing its violation. Notice that rather than finding a counterexample that violates the Lyapunov condition, we find the worst counterexample that has the largest violation through optimization. To find such a worst counterexample, we notice that V theta x is a piecewise linear function of x. Both functions we want to maximize also become piecewise linear functions. It is well known that we can solve a mixed integer linear program to maximize a piecewise linear function. As a visual illustration, let's look at a plot in the bottom. You could think that we assign binary variables for each linear segment to indicate whether that linear segment is active or not. We can reliably solve the mixed integer program to global optimality with very high accuracy. Previously, researchers have used mixed integer linear programs to find counterexamples for neural network in applications like image classification. In this paper, we apply this idea to control theory, and instead of just finding counterexamples, we will improve the neural network from the MILP results, such that at the end of the training process, there exist no counterexamples. So our goal is to find the neural network parameter theta such that the violation of the Lyapunov constraints are 0. To diminish this violation, we define a total loss function. Our loss function contains the violation of the positivity condition solved through MILP, and also the violation of the derivative condition as an MILP cost. Moreover, we include the sample loss of the Lyapunov condition violation as the counterexamples generated from MILPs. Later, we will show that with this combination of loss function, the training converges faster than only using either the MILP cost or only the counterexample sample loss. With the minimized loss function through solving this min-max problem, this is called bi-level optimization, which we can readily compute the gradient of the loss, and then use the gradient descent to reduce the loss to 0. The gradient of the MILP cost is computed using the optimality condition of the MILP. We skip the details of computing the gradient here, and you could refer to our paper for the math. So how does our approach work? First, we show the result of learning a Lyapunov function on a continuous time system. The left-hand side is the Lyapunov function. On the right-hand side, we draw the phase plot of this continuous time system. It has two hybrid modes, with the red line as the boundary of the hybrid modes. The black lines are the boundary of each linear piece in the piecewise Lyapunov function. As you can see, each linear piece doesn't align with each hybrid mode. And we can actually prove that if we were to align each piece with each hybrid mode, then there doesn't exist such a piecewise linear Lyapunov function. This shows the advantage of freely searching over the domains of the linear pieces. We also draw the contours of the Lyapunov function in green curves. You can see that all the arrows point inward into the contour, indicating the Lyapunov function decreases everywhere. We also draw the color map of Lyapunov function together with its time derivative. As you can see, the Lyapunov function is positive everywhere, and the time derivative is negative everywhere. We now apply our approach to a discrete time system. Again, we draw the color map of the Lyapunov function and its time derivative. On the bottom left plot, we draw the boundaries of the hybrid mode in red lines, and the boundary of each linear piece, the Lyapunov function, in black lines. You could see that they don't align with each other, indicating we can freely search for the domain of each linear piece. Previously, researchers have shown that if the system dynamics is changed a little bit, then there doesn't exist a piecewise linear or piecewise quadratic Lyapunov function if each piece were to align with the hybrid mode. Using our approach, which can freely search over the domain of each piece, we can successfully find the Lyapunov function, which we draw the color map below. This shows the advantage of our approach over searching with a fixed domain of each linear piece. Finally, we did an ablation study that we compared the number of gradient descent iterations across different loss functions. First, with only the loss on the counterexamples, which is what people did with SMT solvers, and the one that only uses the MILP costs. And finally, a combination of both the sample loss on counterexamples and the MILP cost. We find in most cases, the one with the combined loss converges fastest. So to conclude, we can synthesize a neural network Lyapunov function for piecewise linear systems. We certify global stability by solving MILPs. The MILP generates counterexamples, and we can obtain the gradient of the MILP cost. The advantage of our approach is that we can jointly search for both the piecewise Lyapunov function and the domain of each piece. The limitation of our approach is that we cannot guarantee to find Lyapunov function, even if the system is stable, as gradient descent doesn't always converge to global optimality. We also have the scalability issue that solving MILP can be time-consuming. We are currently working on speeding up solving MILPs by techniques like warm starting or early termination with suboptimal solutions. This is the end of the talk. Thanks for listening.